Okay, so let's get started. So just a recap of what we did last time, right? So for the past lecture and most of today's lecture, basically what we're trying to do is we're going to try to model a transmission line in the following circuit. Okay, so our goal is eventually to get to this circuit for a transmission line. And so from the past lecture, what we had is, so this is fairly easy. So this is easy to do, right? So this just comes from the fact that your wire is not a perfect wire. And there's some resistance to the wire. There may be temperature dependent, and this number we can look up what the R value is for this wire. Then in the past lecture, we said the inductor, where the inductor comes from is a little bit less obvious, right? So why does the line look like an inductor to us? So the reason that our line looks like an inductor is the following. It's because when you have two parallel lines, right? I say one carrying current this way, one carrying the return current on the line. What a time varying current does, what a sinusoidal current does, is makes look there is a magnetic field around the line. And then these two magnetic fields interact with each other, and basically it makes your line looks like an inductor. Okay, so the inductance comes from the fact that we create magnetic field, and that basically there's some energy exchange in that magnetic field. So this is where the inductance comes from. So all the equations we have seen last time is a little bit, so we just stated the equations basically, right? We didn't really explain where they come from. So for this class, we'll do one question that reminds us how do we use the inductor equations, inductance equations. Then we'll actually look at capacitance. So this class will look at capacitance, and basically, because that is a easier calculation for us to do, it turns out that's the integral is easier for us to do. So this class will look at basically where this capacitor comes from. Okay, we'll look at where this capacitor comes from. And we'll get a set of equations that's fairly similar to the inductor equations. And those two together gives us this sort of circuit-wise transmission model. Okay, so that's the transmission line model. So that's our goal. So again, you'll see some integrals, right? So the thing is to just remember all these integrals turns out to be easy. And what we should remember is the sort of the dependence, right? The dependence of different parameters, right? Not, the exact equations you can look up, but we should remember sort of, does it, when the distance between the, for example, between the conductor gets large, right? Is the inductance larger or smaller? These are sort of intuitive ideas we should have, okay? And so let's do one review question, one real example, basically, to remind us. So let's say I have a three-phase line, okay? And I bundle the two connectors. I bundle the two connectors. So I put two connectors very close to each other, separate out by 18 inches, and have three lines separate out this way. And each of the line has a radius of 0.5 inches. Okay? And we want to find, so go to find the value of the inductance. So find, for example, LA, okay, for phase A, right? We want to know what the value of the inductor for phase A is, okay, for this three-phase line. So as a reminder, the way we do this question is, right, there's two things with this line. One is we have three, okay, we have three phases in the line, and two that we're bundling, right? We're bundling the conductors. So if you look at the equation we have, our equation was that the inductance in one phase is mu naught over 2 pi. This is a constant. Natural log of dm over rb. Okay. So dm, as a reminder, captures how far away the different phases are to each other. And rb captures basically the size of the conductor. In this case, the size of the bundled conductor. Okay. Right? So it depends on these two values. Right? So anybody remember how do we compute dm in this case? Right? So what was the equation for computing this is the average distance between each of the bundles. Right? Remember, how do we take this average distance? So we take a mean, but what kind of mean do we take?
A geometric mean.
Right, so we take a geometric mean. Okay, it turns out for this type of distance, the mean we should take is a geometric mean. So we want to know roughly, on average, how far each conductor is, from one another, right? And then we take a geometric mean. So this geometric mean, as you look at this separation distance, okay, between the three phases. Okay, so, right, so from A to B, we have 20 foot, 20 feet separation, 20 from this two, then multiply by 40 because this distance is 40. Okay, so you can, right? So this is the geometric mean we take. So pretend we're looking at the distance to the single phase, phase A, right? So we're distance of 20, 20, 40 away from each other. Geometric mean means you multiply all of them, you take a cube root. Okay, this is just the definition of geometric mean. So putting all these numbers, we got 25.2 feet of distance. Then RB, right? RB is now looking at how big this sort of single conductor bundle is, right? So how big this thing is. So this again we take geometric mean, right? The geometric mean we take here is the size of each conductor versus the separation between the two bundle conductors. This is the geometric mean we take. So for this RB, right, remember, these are bundled together. So we need to take geometric mean between this radius and this distance. So this is 0.5 inches. This is 18 inches. Okay. And the factor you need to remember is that there is always an R prime associated with it. Okay, so when we talk the radius of the conductor, we're talking about the R prime, not R. So R prime times 18, so this is 0.5 times e to the 1/4 times 18. So that to the square root. Okay, so this is also geometric mean, but when you talk about the radius, there's an e to the 1/4 term that just always come with it. Okay, and if we did the sort of calculation, there's just a constant that pops up, right? So for now, we just need to remember this as a constant we have. Okay, we always have this constant. So doing this calculation, 2.565 inches. Okay. So the thing to remember is that you need to be careful with the units, okay? So especially in the US, the units are normally given in inches for the line conductor size. There's something else for the distance between the conductors. Okay, in something else, you will see sometimes meters being used, okay? But you'll see sometimes, feet being used. Okay? The thing is just to remember, convert them to the same units. Okay, so this is 0.22 feet. Okay? So if one is in inches, then make the other one also in inches, or vice versa, right? So just be consistent with the unit we're using the system. Okay? So this is actually the source of a lot of mistakes on homeworks or in exams. So there's something you need to double check, right? And unfortunately, you do see this kind of standard, varying all over the place. Okay? Especially because US and Canada is one big electrical system, right? But they use different units. So sometimes this causes problems. So there's just something to be mindful of. Then plugging this into the equation, we have this as, so mu naught over 2 pi is 2 times 10 to the minus 7 log of 25.2, 0.22. So this is 9.47 times 10 to the minus 7. So what is the unit of this thing? What is the unit of this inductance? Right, so this, we use this equation, mu naught is some, constant. Then we look at the log of the ratio of the average distance. But what is the unit of this value? Is it in feet? What do you think this unit would be? Right, because you can easily have a follow-up question on this. Okay, we can compute this inductance, but I can say, for a 1 mile long line, what is the total inductance of this 1 mile long line? Then to do that question, we need to understand the unit of this LA, right? Because this is the average value. And we said nothing about the length of the transmission line, right? So this has to be something per something. What is the unit there? What do you think the unit is? Okay, so let's do the easy part, right? So no, it's not per feet. So the Henry is correct, right? So Chess says Henry per feet, no. So this is actually Henry per meter. This is Henry per meter. The reason is the log, the thing inside the log, this whole thing is unitless, right? Because the units divide out, okay? So when we do this division, the units actually cancel. We're taking a log of a unitless quantity, which makes sense. So what controls the unit? Mu naught actually controls the unit, okay? So mu naught controls the unit of this whole thing, right? So 2 pi is a constant. So mu naught has some unit associated with it. But mu naught is, we state this in SI values, okay? So these are in standard units, right? So then what happens is when you do this calculation, whatever distance we used inside the log doesn't matter, okay? So that all cancels. Then what is controlling the unit is a mu naught constant. And for most, we use SI units because for when mu naught is defining SI units, mu naught over 2 pi is just 2 times 10 to the minus 7. Okay? It's just, in some sense you can think of that's how mu naught is defined. Okay? So that's why we have a unit of Henry per meter. Okay? So you do this, you always have a Henry per meter thing left over. Things inside the log just cancel. Okay? The units cancel. Okay? So this is something to remember when you're looking at the equations, right? So again, during the exam is open everything, so you can look up wherever you want to look up the equations. But when you go very fast, you tend to write down, you tend not to be very careful with the units. And then if the question has a follow-up part like, given 1 mile long line, what is the total inductance? You may multiply by the wrong value there, right? So that's something to keep in mind of. Be very careful what the units are for all this kind of things, right? Especially they're given in all kinds of different values, right? All kinds of different systems, okay? Right? And also, so since the exam is open stuff, so you're expected to look up unit conversions. Okay, so in the past, we'll give unit conversion tables on the exam, and from kilometers to miles, meters to inches, things like this. But now, since you have access to internet, so you're excited to just Google everything. Okay, so that's one thing you need to know. If you're not familiar, be sure to know how to find unit conversions of length and weight and different things like that. So any questions for this example?
Yeah, I have a question.
Yeah, go ahead.
Where did you get the value for mu naught?
Oh, mu naught as a this is the constant. So you can just remember this mu naught as 4 pi times 10 to the minus 7 Henry per meter. This is a definition of mu naught. This permeability constant. Yeah.
Is that strictly for aluminum?
No, so this is the mu naught as free space, permittivity for free space, right? Because what determines the inductance is the gap between the conductors, right? So the fact that it's what kind of line it is doesn't enter this. So we should strictly be speaking using the value for air, but it's very, very close to free space. So just this mu naught value. So one good thing to remember is mu naught is 4 pi times 10 to the minus 7. When you divide by 2 pi, you always have 2 to the 10 to the minus 7. That's a constant we have. Yeah, good question. Okay, so this is a value that, again, you can always look up this if you want. But again, be careful with the units. What tends to trip people up in this kind of questions, you see a lot of different units that pops up. Right? You see, we'll say, oh, what if it's a 60 hertz line, 50 hertz line? Right? There'll be a lot of 2 pi's and frequencies and distance units coming up. So just be sure to write down the units at least. Okay. Right. Any other questions about this type of calculations? Okay, so the way you use this kind of equations is not terribly exciting in practice. So in practice, what you do is we have the following case. So how do people sleep? Right? So let's say you go out and you buy a piece of transmission line. Okay, so how do we look up values what does the data sheet look like for this transmission line? So one thing is this is always 2 times 10 to the minus 7. Okay, this is just a constant. Okay. And the way we want to, and often we're interested not so much on the inductance, but on the reactance. So we're most often interested in omega times L. Because we have an AC circuit, so when we use it, we actually use X, not L directly. So this is 2 pi F, 2 times 10 to the minus 7, log of dm over GMR. So GMR is a geometric mean radius. Metric mean. Yeah, go ahead.
So we represent the GMR with the R with the small b, right?
The R with the small d, yes. Yeah, so the geometric mean between R prime and the small d, yes.
Okay.
Okay, so this is against this what comes out in ohms per meter, right? Okay. So actually, what we can do is normally we write things. Okay, so then this is the SI definition. And then often because lines are given in miles, a length is in miles, right? So 100 miles, 500 miles, this kind of length. So you can plug in the mile to meter conversion and break off the log. So this is, since log of you can think log of a product as the sum of the logs. So if you want to convert this to ohm per mile, this is 2.22 times 10 to the minus 3 times the frequency times the log of 1 over GMR plus 2.022 times 10 to the minus 3 times frequency log of d over m. Okay, and this is in ohm per mile. All right, so these are different equations you will see. everything comes from this base equation. You can do the unit conversion directly if you want. Okay, so you don't like ohm per meter, you can directly put in ohm per law. That's a choice.
Professor?
Yeah, go ahead.
What is the, I can't quite read, what is in the last natural log there on the right side of the.
Oh, sorry, this
ohm
is
per mile?
this is the typo, sorry. This is dm, frequency times log of dm. Okay. Geometric mean of large d.
Thank you.
Okay, so the way we do this equation is, right, so yeah, so this is just converting meters to miles, if you will. Makes these constant a little bit larger in front. Okay. But the nice thing of when you separate out these two terms, those two terms separate out into two parts. One is just depend on the GMR, geometric mean radius, right? Doesn't depend on the distance between the two, doesn't depend on actual spacing. And the second part, which depends on the spacing, but this is sort of independent of how you actually arrange the bundles. Okay, so this is, for example, this is if you have two bundle line this way, this XA capture the fact that what does this thing look like? Right? What does this, when you bundle it, how does it look like, from far away? And this is sort of the large spacing between two things, right? So that's the idea of XD and XA. There's two parts. So that means when you buy a line, you can arrange to be whatever, in the bundle, however lines you want. And then you can look at the spacing and they separate into two terms. And they contribute, each of them contribute a part to XA. Right, so these are how the two equations separate out. And the way we use it is normally you're given a table of values. Okay, so what does the table look like? Right, so basically, when you ever go by a piece of line, we'll basically tell you what line it is. All the lines have different names. Sometimes, I don't know why they're all named after birds, actually. So that's one thing. If somebody knows, please let me know why they're all named after birds. I'm not quite sure. But each of them has, named after some bird. You have dove, eagle, hawk, osprey. Yeah, not sure why. But anyways, so you go out and buy them. You look up the code name, and then that gives you a big table, basically, of things you can look up, right? So we'll say resistance, for example, you can look up different resistance at different temperatures. You can take an average temperature your line will operating, get a resistance value. Will also tells you this XA value and will tell you XA value. Will tell you the resistance and the capacitive values. So it tells you all you need to know in this, right? So it'll tell you all you need to know for this line. Okay, so the manufacturer of the line tabulates this. Okay, so tell you GMR, will tell you the XA and things like this. Okay. So all you have to do is go look this up and do calculations this way. Okay, so yeah, do we want to? Yeah, so actually, we don't have to do an example here. So this is just look up the table. And nowadays, nobody actually uses the table anyways. What people do is you just go to a computer, okay, type in the line you want, tell them how far it's separated by, and the computer will tell you the value, all the values you want to know. Okay, so that's the way we do things. Okay, we don't actually. It's hard to find these tables anymore. There's some program will tell you. And one thing is when you actually go outside to measure the value, no, it's never exactly this. Okay, so this bit, you can think of this as the value we can do design by, we can do calculations with, but in practice, the value is always slightly different. And it's often a challenge to figure out exactly line parameters. Okay, so the reason, so for most of the transmission line in the US, when do you think they're built? Let's say you go out and take a look at some random transmission line. How many years ago do you think those lines are built? Are they fairly new? Are they 50 years old?
40 years ago.
Yeah, so most of these lines are 40, 50 years ago. They're not very new. So one issue is that when we build a line, we probably had a table and somebody went to look at this thing, numbers. The system now, after 50 years, who knows what the values are actually. So often there actually is a mismatch between the values. And this is especially true for distribution systems. Because for distribution systems, often you just build a line. Okay, you find a contractor, you build some line, there's some value with it. Normally you don't actually worry all that much about the value of the line. Okay. So nowadays you want, you go to a utility, you ask them, hey, I want to know the inductance of this line that runs under my house. Most utilities probably cannot tell you. And now that they don't want to, they just don't know. Nobody knows what that value is. So as you have, more and more resources like, solar panels on rooftops, you have batteries, you have electric vehicles. Often we actually start to care about the distribution system, want to do calculations there. But a lot of times the first step is I don't know the value of the transmission lines. Okay, there's some line connecting my home to the transformer. How long it is, we're not exactly sure. What type of line, we're not often exactly sure, How wide it is, what kind of line, we may or may not remember. Somebody has to dig up, a paper record that's 50 years old. Okay, so often the first step is actually do an identification of all the line parameters. That is that's fairly active research topic actually. So in this class, we'll be seeing as almost always the question will be, given a transmission line, with all these parameters, calculate the power flow. Often in practice, we start asking the reverse questions. I'm going to put a sensor on my home. I know the power I'm drawing. I know the current. I know the voltage. I need to figure out what the system actually looks like. So I need to figure out sort of this inverse problem. And that's some issue that's not well understood, at least not yet. Okay, that's still a challenge. So when you do this kind of modeling, right? So it's not always as simple as somebody will hand you a good record that says this line, as Dove, that's a mile long. You may not have that. All you have is this are some sensor measurements. Go to and figure out what the system looks like for me. Okay. That's a fairly active research area. So if you're interested in this area, right? So you can go look up some literature here. This is good opportunity for a project. So you're a master's student, you want to do a project. There's sort of enough data now that you can try some machine learning techniques, right, to figure out the system. There's very interesting topics here. Okay? But if you are lucky and you have a good record, all you do is you open up a computer program, type it in, it will tell you all the parameters you want to know. Okay? So next, we're going to look at the capacitance calculation of a transmission line, right? So so you see we'll derive it. We'll look at the path integral. We'll say why that's easy to do. We'll get some intuition of where the logs come out. In all this equation, you see a lot of logs. And question is, why does log come out of all these things? So we'll look at why they come out. Okay. And we'll we'll basically do the capacitance calculation. That will give us a model transmission line. And then there's a quick step to the so-called the lumped parameter model of transmission line. Okay, so let's look at the capacitance on the transmission line. Okay. So this is, again, we're still in chapter 4. So if you read the textbook, chapter 4, there is a lot of stuff, okay, in there. There's quite a bit of stuff. Right? So if you're interested in this kind of modeling, I encourage you to read it. But they're not required to know, for example, for exams or for homeworks. And so you will not be asked to do integral. on any of these things. But if you're interested in doing, how we get this kind of equations, that's something you can read. There's quite a good application of EM theory, EM field theory. Okay? And so where does capacitance come from? Why do we have a capacitor on the line? Basically, it's a duality between charge, between electric field and magnetic field, right? So moving current creates magnetic field. So moving charge creates electric field. Okay? And we're going to look at how do we do calculations with this electric field. Okay? So as a reminder, right, when we have a field, that means if we have a charge we have a charge, we have a field that's radius, we have a field that radius L from the charge. So that's the equation we have. And what drives this equation is basically Gauss's law. Okay? So anybody remember Gauss's law? So I'm assuming you have all seen it. I'm assuming you have seen it. Anybody remember why it's useful? Why is Gauss's law useful for us? Anybody remember that? Right, so the reason why Gauss's law is useful is basically given in this equation, okay? Gauss's law is useful basically saying, look at this thing on the left-hand side. Look at this thing on the left-hand side. Nobody knows what this is, right? At least when you look at it. This means a closed integral around a charge. That's perpendicular to, that's integrating over the electric field. That's perpendicular to it. That may mean something to you, or it may mean nothing to you. What Gauss's law says is, you don't need to worry about this integral. This is just equal to the total amount of charge you have. Okay, so instead of doing this fancy integration, all you need to do is count or measure the amount of charge you have. Okay, so this says instead of doing integral on the surface, just look at the charge we have. So this is something we know how to do. Okay, you give me a wire, I know how to measure how much charge is moving on it. I may not know how to do this integral, but I know the amount of charge on it. So that's something we can do. The Gauss's law says you have something that's very complicated. You can think of this as something that's very simple. Just counting charges we have. And there's a bunch of constants we have. So this is epsilon naught as permittivity of vacuum, right? So remember we have mu naught for the magnetic field. So here we have epsilon naught for the electric field. And just some number, Faraday per meter. And then for air, we're going to assume it looks roughly like a air is roughly like a vacuum. Okay? So epsilon for air is epsilon naught. All right, so now basically, where does the capacitance come from for a conductor? Capacitance comes from the fact that I have some conductor. Okay, I have some conductor. Because I have charge moving in this conductor, right? We're moving current, so we're moving charge. This creates an electric field around the conductor, right? Charge creates field. Okay? And this field basically makes look like a capacitor for us, right? There's some field. Capacitor works basically, you have a field between two conductors, okay? So I have one conductor, I have some field around it. I want to understand what's the behavior of this field. Okay, so, ideally, we need to do this integral, right? But now we're going to do this integral basically by along the conductor. We do this integral taking advantage of symmetry. We take advantage of the symmetry of the system to do some simple calculations to understand where the logs come from. Okay, so remember in the inductor calculations, we saw a lot of logs and understand where the logs come from. Yeah. So let's look at different symmetry we have. Okay, so let's look at what different symmetry we have in this field. Okay. So if you look at symmetry, okay, so let's say I have this piece of conductor carrying some charge along this conductor, where must all the field point to? Okay, so if I look at this conductor, let's say this is the cross section of the conductor. Let's say this is a field coming out of the page. Where does the field lines point at? Okay, so I have some field. Field is actually, in principle, some three-dimensional stuff, right? Three-dimensional vector field. But if you have a conductor, and it's a symmetrical conductor, means it's the same charge along the conductor, then where does the field point to if I look at the cross-section of this conductor? Can the field point this way along the conductor? Can field point this way? Can electric field point like this? No, right? This breaks the symmetry. Because this conductor is symmetric, so we cannot have a field going into one direction or another along the conductor. Okay, that breaks symmetry. Okay? So the only way the field can point that does not violate the fact that we have symmetry, everything is symmetric along the conductor, the field must point basically radially out of this conductor. Okay? The field must be radial, basically perpendicular to this conductor I have. All the field must be perpendicular to it. Okay? Right? This is the only way the field can point. This does not break symmetry. Any other direction, this point will break symmetry. Okay? So without knowing any about this equation, at least the symmetry argument gives us this. Okay? So instead of looking at a three-dimensional thing, all we need to do is look along the radial direction. All we now have to do is looking along one direction that's radial or perpendicular to the conductor. We don't have to look at other directions. So this is what symmetry bias is. Basically, that's what this slide is saying, right? So as charge on the conductor creates field, by symmetry, this thing must be radial. Okay? So now when we do the integration actually becomes fairly simple to do. Because instead of this weird looking thing integral we have to do, now all we have to do is basically we have to integrate. So this is a normal integral now. Okay, this is a standard one-dimensional integral, scalar integral. This integrating over the radial direction. Okay. So instead of a surface integral, which we have to do for a normal so if we don't have symmetry, we have to do a surface integral. Here, because we have symmetry, our integration becomes simpler. Okay, becomes simpler. So let's look at what this thing actually becomes. Okay, let's look at what this thing actually becomes. So we're interested in the following quantity. Okay, we're interested in the following quantity. We're interested on how big the electric field is. Okay, we're interested in how big the magnitude of electric field. So that means I have some line carrying charge, and I move a distance x away from this line. Okay, so this is a distance x away from line. Okay. And I want to know how much field do I measure when I move a distance x away from this line. Okay. Right? I want to know. Okay. And basically, Gauss's law says the following. Okay, Gauss's law says the following. Consider a cylinder, that's 1 meter long. Consider a cylinder, that's 1 meter long. Okay. I know this is the total charge. This is the total charge inside the cylinder, inside the conductor. Okay. This is total charge inside the conductor. This is equal to the value I get by measuring, by integrating the electric field along the surface of the cylinder, okay? Along the surface of the cylinder. So in other words, this is saying if you draw the cylinder. This is the surface I want to look at. The size of the cylinder, the radius of the cylinder is x away, right, from the wire, from the conductor. And I'm enclosing a total charge of Q. So Gauss's law says when you integrate over this surface, you will get Q. You'll get Q. So we know the following thing, right? We know the following thing. We know Ex, this is constant over the, so this is a constant value. Because we're looking at the surface of the cylinder, we're looking at the surface of the cylinder. The cylinder is the same distance, the same radius away from the conductor. So Ex is actually constant. It's actually constant. This 2 pi x. So what do you think this 2 pi x is? To see how many people is actually still here. So where does 2 pi x from? I have a cylinder. I want to basically integrate over the surface of the
circumference.
Cylinder. Is the
circumference,
right? This is circumference of cylinder. Multiplied by 1, this is the length. Right, so remember, we're integrating over a length of 1 meter. That's 1 meter. So the electric field multiplied by the surface area of the cylinder equal to the total charge Q. This is the total charge Q. Right, so that's what this equation tells us. If you rearrange it, we have something nicer to look at. Basically, it says the field decays as 1 over x, where x is the distance away from the conductor. And there's a bunch of parameters that comes in. What you're observing this parameter is 2 pi shows up. Okay, so where does 2 pi come from? This is where 2 pi comes from. Okay, the circumference of a circle has 2 pi in it. Okay, so that's where 2 pi comes from. Epsilon, remember, is a constant, is a free space permittivity. Q is the total charge I have. X is the distance, how far I'm away from it. So this is at least a very intuitive equation to look at. As the more charge I carry, the larger the electric field. But the further away I am from it, less field I see. Okay, so this is the proportional relationship. It's linearly proportional to amount of charge, inversely proportional to distance. Okay. That's what the equation tells us. So as a sanity check, okay, what happened to the end of the cylinder? Right, so if I have a cylinder, what we did is basically we integrated along this surface. But what happened to the 2 ends of the cylinder? So it looks like my integral just ignored it. Does the end of the cylinder matter? Do I have to take that into account? Why not?
We have the same amount of current entering and exiting, so they cancel each other out.
Almost. This is along the right line of thinking, but the more rigorous reason is, remember we said all the field point radially out of the cylinder. So when you integrate along the end, there's actually no field along the end. Okay, there's no field coming out of this. Okay, there's no field coming out of the end. So you do this integration, right? This integration says you integrate along the field that comes out of the surface. But because all the field comes out radially out of the conductor, there's no field that comes out to ends. So I don't have to integrate because it's 0. Okay? The amount of field comes out is 0. So that's why I can talk about the enclosed charge. So I am enclosing 1 meter long line, but I don't have to care about the 2 ends of the line. Okay? There's no integral there. The integral is 0, basically. Okay? So that's why we can ignore it. And we're left over with this sort of nice looking equation. Okay. So we're getting, so this equation, after we get this equation, things will be easier from here because we have the field, right? So remember, when we talk a capacitor, we're not really talking about the electric field as much as voltage, right? So think of the governing equation for a capacitor. It's not field. We'll talk about voltage, right? dV dt. Okay, so we need to relate. So we need to go from charge to field to voltage to current. Okay, so we need to talk about voltage, not exactly field. But voltage to field is fairly simple, right? Fairly simple. So all we have to do is for voltage is we have to basically the integral of the electric field is the voltage, right? So for example, if you go from 1.1 to 1.2, another point in space 2, then the voltage between those two places, this is just you integrate, the electric field between these 2 points. That's how you find the voltage difference, right? So voltage difference is we go from one point in space to another point in space as how much energy, right? How much potential energy you have, the difference between potential energy, and that is the integration between these 2 points, okay? And the neat thing is for this is, so if you look at this, does it matter if I go, let's say, this way? Does it matter, let's say, if I go this way? Does it matter if I go, this sort of this way? Does the path matter for this integral, right? For potential? No, right? So the path doesn't matter, right? So the thing to remember is this is independent of the path. Okay? So how you get from one point to another point in terms of potential doesn't matter. There's the same analogy as how you climb a mountain, right? As long as you have the same starting and ending point, the net changing potential energy will be the same. Okay? So it doesn't matter which path you took. And so there's some, there's deep, not very deep, but there's sort of a mathematical reason behind this. But now what we have to remember is we're talking about a potential field, electric potential. So the path is independent to the path. Okay? Because it's independent to the path, all we have to do is a simple integral. Because we're moving from one point to another point. I don't care what the path is. All I want to know is how far they're away from each other in terms of this radius, right? In terms of this distance. This is how I care about when I look at the potential difference. Okay, so I don't care how you got from P1 to P2. All I care about is how far they're away from this conductor. With this, I can do an integral, and I can find the potential difference between these two things. So let's do the calculation before we break, because we're very close on how we get the log. Okay, we're very close on how do we get the log thing out of it. So let's say I have a charged conductor. Okay. One point is D1 away from the center of the conductor. Another point is D2 away. And I want to know the voltage difference. Okay, I want to know the voltage difference from 1 to 2. Okay, I want to know this voltage difference. So I do an integral. Since the path doesn't matter, right? Only the distance between 1 and 2 matters from this. So all I have to do is integrating from D1 to D2. Okay, only this matters. The distance there from the center matters. Ex dx. Okay. But Ex, as a reminder, this is Q over 2 pi epsilon s x. Okay. Another way you can understand this integration path is the only place you build up potential is go from one radius to another. Along this path, there's no change in potential because the field is pointing outward, right? The field is pointing outward. So you go along at the same radius, then the field doesn't change. So we just have to talk about integrating from D1 to D2, the distance from the radius. So this is D1 to D2, Q 2 pi epsilon x dx. Okay. And what is how do we integrate 1 over x? that's just log of x. Okay, so the log comes from because it's the antiderivative of 1 over x. So this is q 2 pi epsilon log of x evaluated at d1, d2. Okay. So this we get q 2 pi epsilon log of d1, d2 minus log of d1, or equivalently q of 2 pi epsilon log of d2 over d1. Okay. So this is where the log shows up, basically. Okay, so if you're wondering why there are so many logs in the things, and why is the log of distance of one thing to another, this is why it's log of distance of one thing to another. Okay, just because we have a radial field, we're integrating basically something that's inversely proportional to the distance, and the derivative of a log is 1 over x. Okay, so that's, and 2 pi comes from the fact we're considered a cylinder, so that's where 2 pi comes out. Log comes out because this is how the electric field behaves, okay, and plus some other constant we have in front. Okay. So this is the integral we have, and from now on we'll just go with equations like this. Okay, so from now on, if you forget where the equations come from, we should remember as basically the way we can get an equation, this clean assumption we made is basically we are integrating over a wire, and the field is just radial, right? It's perpendicular to this y, and that's what makes that's what makes the equations work. Okay, that's where 2 pi and log come from. Okay. So let's take a break. Afterwards, we'll do basically the same. We'll look at the same situations we looked at for the inductance case. We'll look at capacitance. All the equations will look roughly similar to each other. We have some geometric means also, but that will also be similar to the inductor case. Okay. Right. So let's break to 10:33, then we'll come back at 10:33.
Professor?
Yeah.
I have a question.
Sure.
So I was watching an example on per unit example conversion, converting a circuit. And when they were doing it, it was a pretty basic circuit. It had a generator and then a transformer 1, transformer 2, a load on transformer 2. But when they were doing it, they ended up calculating like the zone 2, the region 2 voltage, which they called was between transformer 1 and transformer 2. And then they found that impedance per unit, and then they found the impedance per unit of the load. And then they went on to pretty much say the equivalent circuit was just those two things in the generator in a circuit, and they kind of left out any impedances in the transformers. And I was really confused in why they did that and how they could call that an equivalent circuit. And I was wondering if you had, I have it pulled up on my screen. If you want me to like show it to you, I can do that.
Sure, can you share actually?
Yeah.
Let me give you permission to share.
Okay.
So wait. Okay, so share, try share.
So this was the circuit that they had here. Oh no. This was their circuit that they had. And before this, they had, shown like how to calculate the different voltages in each region and things like that. And then this was their equivalent per unit. It was just this.
So if you go back to the circuit, did they give values for the for the transformer reactances? Did they give any value, or they just stated this as a?
They gave values for I think that actually this has been a string of several videos, so I can't quite remember, but I'm pretty sure I remember them giving like a power rating and a like you know, I mean, I guess it's 1 to 10, so I don't have to really give the voltage ratings, but
Right. So I guess for this, it may have assumed ideal transformer looking at this. It may have assumed ideal generator because the generator doesn't have a synchronous reactance.
right.
Right, so they may have assumed ideal generator, ideal transformer. So the only thing there is a turns ratio that does voltage conversion.
Okay.
So then the line is the only thing you have. Or they may have just reflected already built into the line. That less likely, that's less likely. Or more likely, it looks like they just assume this is the ideal transformer.
Okay, because we're not going to be dealing with ideal transformers in most.
No, so when we do this, no, so the resistance often we just ignore, but reactance on transformers and generators actually are not that small. Like they'll be fairly significant if your line is not very long. So for a short, no, if the line is not terribly long, the synchronous reactance of the generator and the reactance from transformer actually contribute significantly to it.
Okay.
It's not an insignificant part of it, so we normally don't ignore it. Looking at this line values, I suspect if this is a practical numbers, the line is a pretty long line. Like 20 ohm is not as small, it's not a short line. So they may have thought, you know, the number they just compute, okay, the line is long enough that would dominate all the other values, so let's ignore others. Right. So but normally for lines that's not this long, like 20 ohms is a large value for long. Like whenever your line dominates your load, then that's a long line, right? So
okay, so yeah, they're pretty much just looking at just looking at it from an ideal standpoint, and okay, all right, thank you.
Yeah, no problem. So then All right, so let's get started again. So before we go on for the class, actually, so let's look at some dates for the midterm, some potential dates for the midterm. So one day we can, so two possible dates. One is Monday, November 2nd, or Monday, November 9th, right? So both are Mondays. So either the first Monday in November or the second Monday in November. Anybody have some preference for which day it is?
Second Monday. I have a test on the first Monday.
Okay, all right. Anybody against the first Monday? The second Monday? All right. Okay, second. Everybody says second. Okay. All right, so we'll set it for the chart. Okay, all right, second Monday. So okay, so we'll set it now for the 9th of November, right? Second Monday. Okay, so I'll send the official email out for that. Okay, so we won't know exactly what we cover probably until we get closer, but you know, we'll have a rough idea what to cover, probably what the midterm will cover next week. Okay. Right, so those will be again fairly you know, format-wise will be fairly conventional midterm. Questions, you do some calculation, you write an answer. So the only difference is that you can use computers, you can Google stuff if you want to. Right? So I guess if you prepare, you know, prepare knowing the technology you have access to. Okay. Right, so if you have some issues, let me know. Also, you can email me. Right, you can also email me if you want. So if you cannot do it in class or you have some other situations you want me to be aware of, please let me know. Email, let me know. Okay. So for the people in Asia who's watching this later, so your exam will be fairly similar time, the same day, but a different time of the day. All right, so that's a midterm date. Okay, so let's continue with the voltage calculation we're doing. Right, continue with the voltage calculation we're doing. So let's look at when we have multiple conductors. Okay, so we never have a single conductor in a power system. We always have more than one. Okay, so let's look at what happens when we have multiple conductors. Okay, so here this is the following picture. This as carrying charge. So let's see. This is charge of Qm here. Okay, so this conductor carrying Qm. I want to know the voltage difference. I want to know the voltage difference between another conductor, K and I. Okay. So this is, we have some conductor carrying charge. There's two other conductors around it. And what I'm interested in is the potential difference between these two conductors, So the calculation we did last time, right, was around a charged conductor. Okay. So now I want to compute the voltage between two multiple conductors. So this is not very difficult to do. Okay, this is not very difficult to do. And the reason it's not very difficult to do is we can use superposition. There's a nice thing about this kind of system. It's actually, in some sense, linear. You can add things differently. Right? We can use superposition in the way that we know the voltage, for example, between K and I, is equal to the voltage between K and M, right? So plus the voltage between M and I. This is the equation we have. Right? So we know right? We can compute voltage by going back first and coming down this way. this is equivalent to this voltage. Okay. Right. So we don't need to compute directly between K and I. We can use superposition and compute it both reference to M, and just simply add the voltage when both of them reference to M. Okay. So when you add the voltage, when you use superposition, what we have is this voltage is simply the 1/2 pi epsilon. Right? So we can have is log of di over dk. Okay. So this is our voltage superposition between these 2 points. And we have multiple conductors. Right? So multiple M, labeled by M. And then this Ki is simply 2 pi epsilon sum of Qm log M equals 1 to capital M, log of the distance I to M, distance K to M volts. Okay, so this says if you have M1, let's say M2, all carrying current, M3, all we need to do is to sum up the contribution individually at a time. Okay. So we don't need to actually think about the different, we don't have to redo the calculation for when the configuration of the charge carrying conductor changes. All we need to do is just to sum up this contributions individually. Okay, so then let's look at an example. Okay, let's do a calculation for a single phase 2 wire system. Okay. So this means one of them, right? So we're carrying current on one conductor and return current on the other conductor. Okay. And I want to figure out the voltage. Okay, the voltage. So the picture here is at some point, that's X, at some point, that's Y away. I want to calculate Vxy. Okay, so I want to compute this voltage. When there are two conductors carrying equal and opposite current. Okay, so this is what we want to do. And then when you look at these equations come out to be this way. Okay, you basically compute. Right, so let's be a little bit better. Okay, so let's call this conductor X, call this conductor Y. We want to know the voltage difference from X to Y. We want to know the voltage difference from X to Y. And when you plug in into equations, you basically plug into the voltage equations. That's what we get for Vxy. So if we want to make some simplifications for this, we'll assume, right? So the distance between the two conductors is d, and the radius between the two conductors is r. Okay, there's r. So I have some point x on the surface here, some other point y on the surface here, and we want to compute the voltage between x and y. Once we start plugging into the equations, well, we have the following: Vxy. This doesn't change, 2 pi epsilon. This is log. The d's are the same, so this d times d, this is r times r. So this is q2 pi epsilon log of d squared over r squared. Q2 pi epsilon log of d over r squared. Okay. When you log something, when you log of squared is the same as moving the 2 to in front of the log, d over r. So this is equal to q over pi epsilon log d over r. So this is for a, okay, this is the voltage difference when we have 2 conductors carrying current. We get it by plugging numbers, right? Just plugging all these parameters into the equation. So we're almost to capacitance, right? We're not exactly there yet because we're calculating the voltage difference. We're calculating the voltage difference.
Hi,
So
Professor.
Yeah, go ahead.
So how you get the things inside the natural law, like the dyx over dxx and the dyy over dxy?
Right. So the dxy, right, is how far away they are from each other, right? Dxy, the distance between x and y. And that's just the distance between the conductor, so that's just d.
But how you get the relationship, like the why you plug the equation and get the dyx over dxx?
Oh, how to get to this equation? Okay, so let's look at, okay, so let's try to derive this, right? Okay, so you have a point on x, you have a point on y, right?
Yes.
Right, you have this, okay? So I want to compute the voltage, right? So let's first compute this, right? Let's say, okay, so let's look at this equation, okay? So this says I have a surface, I have a point x here on the surface. There's r here, right? So this is r. So dxx, this is this distance, dxx. Okay, how far I'm away from this point, charge q. Okay, this is dxx. This is how far I am away from this q. Then I have another charge carrying, right? Okay, I have another thing here, minus q, and this distance is d, let's say y xy, okay, dxy here. How far they're away from each other, right? When I'm looking at this potential on x, right, I'm impacted, right? There's 2, okay? Looking at this point x, okay? So I have a 2, so look at this log equation, right? I want this potential from x to y, okay? So there's 2 distances. One is the distance I have, so look at the q log dyx, dxx, okay? One is the distance I have from this dxx, right? And when I'm looking at something far away, this is y here. This distance y, this is dyx, right? So remember our equation as q, the amount of charge, times log of this distance yx divided by dxx, right? This is basically was our single conductor equation, d2 over dy. So here d2 is dyx, d1 is dxx. Okay?
Okay.
Right? So for the other one, you have this equation. It's a minus q because it's carrying the opposite charge, right? So for this equation, what you have is, right? So you have some point x here, right? You have now, this is y. Okay? And you're measuring, this is where minus q is, right? So here, your d2 is a distance between y and this point. This is dyy, or this is called dyy. d1 is a distance between x and this point, so this is dxy. So you get minus q because it's carrying, charging the other direction, log of the ratio of the 2 distance. Then you put them into one equation, you combine them, you get this equation.
So which means you calculate the distance between the, the voltage difference between the x and the y. For the first part, you consider x as the point, And it's just a potential difference between the x and to the core and the x to the y. And second, you move to the difference in the y point. And it's only like to consider the y to the inside the core and the y to the x distance. But y is like the first the y-x, but not the
okay. Right. So this is saying I'm only computing the potential difference from x to y, right? I'm not computing the potential difference from y to x, right? This is only x to y, right? This is measuring only x to y. And this potential is contributed by two charges, right? One is a charge carried in the x conductor. Another part of this is contributed by the charge carried in the y conductor, okay? So if you look at the potential from x to y, there's two things that contribute to it, right? The fact that the x wire is carrying q. Another comes from the fact that the y conductor is carrying minus q. Is that clear? Is that okay?
I'll ask later.
Okay, so basically, right, so here is, right, so we have two wires, so there's two fields, right? So the wire, two conductors, two fields. The x conductor is carrying, this conductor, this q conductor is this, let's say, positive q. This is a conductor with a charge, so that creates some field. This is a minus q, but that's also creates some other field. So you talk about the potential between two distances in the space, both of them contribute, right? So that's why there's two terms inside the bracket. Okay, that's from x to y. And then if you plug in some simplifying notation, basically, you get pi epsilon log of d over r, right? And basically, this two comes from the fact that you have two wires. Okay, so why did this two come from? And this two is from the fact that you have two wires. Okay, so twice the potential, right? Twice the potential this way. All right. So this is the voltage between the two wires. And then how do I get from voltage to capacitance?
I have a question.
Yeah, go ahead.
Can you go like 3 slides back?
3 slides. This one?
No. 2 forward now. To the next one.
Can you see the number? 13?
The one after that.
14? Okay.
Yes.
Yeah. Okay.
Sorry, I can't see the number for some reason.
Okay.
Is there the first equation that you wrote, is there supposed to be a q in the numerator before the natural log?
Yes. Right, yes. Q. Yeah. I forgot the q. Yes, there's always a q. Yeah, that's a charge. That's a charge. Yeah. Forgot the q.
Hi, Professor.
Yeah.
Can I go down one more slide? So for this one, which is the k and which is the y, k and which is the I, in terms of x and y?
Okay, right. So k is x, I is y.
I is y. Okay.
Right. M, there's two conductors. So M is both x and y. Right. So two conductors.
So what is the m?
Right. So M is the number of conductors we have, right?
Okay.
So M denotes the charge carrying conductors. So here both x and y conductors carries charge.
Yes.
So we're only computing the voltage difference from x to y, vx y. So there's two conductors carrying charge. So there's two terms in the sum.
Okay. So I think the DIM and the DKM, I don't know which the DIM like the y becomes the YX and the DKM becomes the DXX.
Okay, so let's say, let's see if we can insert it. All right, okay, all right, so let's make substitution, right? Let's say M, So if you want, right? So K as X, I as Y, M as X and Y, right? Okay, so let's say first K equals X, I equals to Y, M equals to X. Okay?
Okay.
All right. So DIM, what is this? This is D YX, right?
Yes.
DKM, this is DXX.
Yes.
Right? So then you have second K equals X, I equals to Y, this doesn't change. M equals to Y, right? So DIM as DYY, DKM as DXY. Okay?
Yes.
Yeah, so this is just accounting for the distance, right? So you plug everything in and reduce the log. It's just that ratio. Any other questions about this? Right, so yeah, this can be a little bit confusing. So if a question, yeah, please ask. So is this just, yeah, so this sums up basically the, so for each conductor, you have this log term, right? And just computing the ratio of the distance between the 2 points X and Y.
So Professor, the reason that we have the different positive and negative Q on the wires X and Y
right.
is because their currents are going opposite directions, right?
Right, yes.
Okay.
Right, yes. Right, so one, yeah, go ahead.
Professor, why we make M equal to the X and the Y?
Because I have two conductors, right? The X conductor is carrying current. The Y conductor is also carrying current. And I want to know the potential difference between these two conductors. So I have two conductors carrying current, right? So I'm measuring the potential between the two conductors, right? And the potential I'm measuring is from one conductor to another. So if M denotes the charge carrying conductors, then they're X and Y, right? So this is X, this is Y. I'm measuring this potential difference.
Okay, thank you.
Right? So if you want to draw, so if this is easier picture to draw, think of this X wire, this is Y wire. This is carrying Q this way, this is carrying Q the other way. So this is minus Q. All right, so yeah, this is one is Q, one is minus Q. Right? And what we want is this potential difference V of XY. Okay, so if drawing this vertically helps, this is the mental image you can have. This is slightly, analogy slightly misleading because as you know, looks like there is a, looks like there's an order between X and Y. There's really not. Right? So, but this, if you want to think of vertically, think of this way. Right? One's X, one's Y. There's some voltage difference, right? Because they're carrying different, because they're carrying Q and minus Q on these two wires. And they're carrying charges, there's some potential difference. And the potential difference is both wires contribute to the potential difference, right? Both of them contributes to it. One, right, so I have contribution because X is carrying charge, I have another contribution because Y is carrying charge. So if you do the calculation, you have a 2 that comes out. That basically comes out because you have a square in the middle. Or you can think of it as because you have two terms. Two terms in this. Okay. Any other questions? All right, so these are good questions. Good questions for this. All right, so okay, so so I guess the thing to remember is we're always measuring potential difference between wires, right? So we don't care about the potential difference between some random 2 points in space, right? Because we're trying to do a circuit model where the things in the circuit model are transmission lines, right? So we care about, for example, the inductance on a transmission line. We care about the capacitance between 2 transmission lines, right? These are the things we care about. So I guess that's why, you know, M is also X and Y, right? So the charge carrying conductors are at the, you know, are the points where the potentials we care about, right? There. So they are the same, right? Okay. Right. So finally, we have capacitance. Now we want to move into, we have voltage. We want to move into capacitance. So what's the equation between capacitance and voltage? Do you remember the basic equation? What is C? X and Y? From basic circuit theory, if my voltage is induced by charge Q, what is my capacitance? Basically, how do I get rid of this Q? Right, so you look at this equation. All the numbers I can calculate, pi I know, epsilon is a constant I can look up. D and R are the parameters, right? Right? Yeah, C is Q over V. So here what we have is Q over Vxy, right? So I need to divide the charge out of it, which is nice because we don't know what charge is. This is not a number we know. But once you divide it out, once you talk about capacitance, now we're okay, right? Because now we have, this is farad over meters. This is per meter long, how much capacitance I have, right? So the constants is pi epsilon, and the geometry, spell geometry wrong. The geometry is D and R, right? So based on how, you know, how thick the conductor is and how far away they're apart, you can calculate some capacitance value. There's some capacitance. So the value is, so basically larger the D, the larger the smaller the capacitance. Larger the small r, the larger the capacitance. So these are just the values we have. Capacitance between a single two-phase line. Right, and then the only thing we need to be a little bit careful about is that often there is a neutral between the line. Okay, so often what we have is we may have a neutral between the line. So for example, you can have a neutral tap, okay, a grounded center tap within the line this way. We have a transformer. Okay. So this happens when, for example, okay, this happens, for example, where you put where you have something in the middle. Okay. So for example, if you look at your house, right? So what is the voltage going into your house? It's actually 240. Then the way you make a 120 circuit is you put a ground in the middle. Basically, you're grounding in the middle. Okay? This is what happens when you have a transformer. Okay? So the question is, if you put a ground in the middle, and you look at the capacitance now to ground, okay? So the capacitance from line to line is Cx and Cxy. Then if you look at the capacitance to ground, why is it 2Cx and 2Cxy? Why is the capacitance larger? Okay, so you have two lines, x and y. There's some capacitance CXY. Now I can ground this. I can do a center tap, basically. This is often what you do is you have a transformer. And you put a tap in the middle and you ground this. This is your neutral. Then why is this capacitance 2CXY? Any reason why this 2CXY? 2CXY?
Because of the distance between the wires?
Because of the distance between the wires, not necessarily, right? So imagine that, so this normally comes out of a transformer. So what you do is you basically have a transformer. All the transformer does is have a 3-terminal output and grounds this. So not necessarily the distance is half, but what happens is the voltage is half, right? So this is Vx over 2. So normally when you do this kind of center tap is you have the voltage on each xy. Between Vxy, you reduce the voltage by 2. And then C since C is proportional to Q over V. When you reduce V by 2, then the capacitance goes up by 2, right? So this is the capacitance. The neutral capacitance is actually 2 times the capacitance between the two ends of the wire. And this is 2 pi epsilon over log of D over R, if you center tap this. And the reason we specially point this out is almost for all the residential houses that we have, this is what we do at your house. So when the line goes in your house, you have a 240 line, actually. And so there are some appliances in your house, for example, require 240. Some kitchen appliances require 240 voltage. But then for the other things that requires 120, you basically have a graph, have a neutral. You basically have a neutral in the middle of the two voltages. And this has the impact, if you look at this as a circuit, this just doubles the capacitance. Okay, this has the effect of doubling capacitance. Okay, so, and this is good thing to remember as the voltage goes down, the capacitance goes up. Okay, because if you're carrying the same amount of charge, right? So this assumes you're carrying the same amount of charge, then voltage go down, the capacitance go up because it's Q over V. Right? Okay, so this is just the one calculation that we often do for buildings. Okay, so buildings normally have this center, has this grounded center tap. So if any of you, ever build a house or do some electrical work or home, you'll see this kind of tap. Okay, so let's do one example. Let's do some exercise. So put some numbers into this. Okay, so let's say I have a 240 kV line, 20 miles long. Okay, and the conductor diameter, so this is R, this is D, and we want to compute the line to line. We want to compute the line to line, sorry, this is not R. So this is 2 times R, right? Diameter is 0.552 inches, so the radius is half of this. The separation is big D, and we want to do some calculations, figure out what the capacitance is. Figure out the capacitance is. So let's do this line-to-line capacitance calculation. So first, let's compute the radius in terms of feet. 5.2 over 2, change the diameter to a radius, times 1 over 12, okay, feet per inch. So this is 0.23, sorry, 0.023 feet. So when we have CXY, right? So this is our pi epsilon over log of D over R. this just comes out to be plugging the numbers, pi times 8.854, 10 to the minus 12, log of 5 over 0.023, 169, minus 12 farad per meter. Okay, so that's the capacitance of the line per meter. Okay, this per meter. So if we want to now do the capacitance for the 20-mile long line, this is the XY. Basically, it's just a meters to miles conversion. Okay, so 159 times 12 farad per meter times 1609 meters per mile times 20 miles. This is 1.66, 10 to the minus 7 farads. Okay. So this is the standard calculation we'll do. And all this calculation, unfortunately, the hardest part is actually unit conversion. And that's the hardest part. The equations are all fairly easy to use. It just everything is given in different units. Okay, we use the constants are in SI units. The distance are in feet and miles and inches. So just be careful with the unit conversion, right? When you use this equations. Then we can ask, right? Then we can ask that what is the line-to-line admittance at 60 hertz? Right. So remember, when we're using a circuit, we need to do the following calculation, right? So the Y, the admittance, actually is frequency dependent. It's frequency dependent. So this becomes J 2 pi times 60 times 1.66 times 10 to the minus 7. So this is J 2.27 times 10 to the minus 5 Siemens line to line. And this is Siemens line to line. It's just the, when we're using it for, again, in a circuit analysis, this is what we do in a circuit analysis. And then if you look at how much reactive power is consumed by this, so how do I compute the reactive power consumed by this? Q, I say X, Y. Right, so now we can pretend, basically. Now I have two lines. This is, I have a capacitor. This capacitor has an admittance value of Y, X, Y. So we have a capacitor of those two lines that consume some reactive power. And how do you compute the amount of reactive power that's consumed by this capacitor? Remember? So how does reactive power depend on the admittance?
Voltage squared times admittance.
Voltage squared times admittance, right? But remember so Q is V squared over X, but Y is 1 over X, right? Admittance is 1 over X. So this is Y times V squared. That's Q. Okay. So this is YXY times VXY squared. So remember, we said this is a 20 kV line. And the voltage of the line is always given by line-to-line value. So that's VXY. So this is 6.27 to the minus 5 times 20 kV squared. Plugging the numbers, we get is 25.1 kilovar. Okay. That's the amount of power consumed by the line. Okay. So when you have transmission lines, again, they have inductors and capacitors. They can be modeled by inductors and capacitors. And in practice, what is the impact? Well, the impact is they just consume reactive power. They just consume reactive power. So when you have a generator, your generator needs to generate reactive power. All right.
I have a question.
Go ahead.
Is the voltage supposed to be 240 kV?
Where did 240 come from?
Oh, 20. Okay, I read it wrong.
Yeah,
Thank
sorry.
you.
Yeah. Yeah, so 20 kV line, right? So that's use voltage. So this voltage basically has nothing to do with the capacitance value, actually, right? This voltage is only related to the amount of reactive power consumed. Right? The capacitance value is independent of the voltage the lines are operating at. But when you want to compute the reactive power consumed, then it depends on the line-to-line voltage of the line, the line-to-line voltage of the transmission line. Okay? So let's see. We want to do three-phase. Actually, no. So let's stop here today. We'll do three-phase lines. It's the same calculation as before, but requires some accounting of the distances. So I think it's better to do that accounting carefully next time. Okay, so we'll do the three-phase line capacitance calculation. We'll do that carefully next time. So to make sure that we know when things cancel for three-phase. Okay. So next time we'll do that. Then next time we'll get the circuit model for transmission lines. Okay. Then basically we'll be done with first part of the class because we have everything we need to build the circuits. And the second part of the class will be to analyzing that circuit. Okay. So you look at the midterm, given the timing of the midterm, there'll be a lot of this part is how do you compute all the different parameters we have in the circuit, right? How do you do, for example, inductance calculation? How do you do capacitance calculation? How do you do the per unit things for the transformers and so on? And a little bit of large scale circuit analysis. That's the thing we'll have on the first midterm. And on the final, we'll just wrap everything up. Everything will be on the final. Okay, so that's the division between midterm and final. Okay. So again, homework due on Wednesday. So have a look if you haven't started. Any questions about the homework or the midterm? Right. So for the midterm, since you're using computers, so I'm assuming you can do basically logs and cube root, square root, whatever nth root, right? I'm assuming you can do all those things, right? So if the only thing, right? So I'm assuming you have more than a simple calculator. At least you have a scientific calculator available to you. That's the assumption I'm making. Okay? So you have some ways to solve equations, right? To do this kind of log calculations and square root and different nth root calculations. Okay? Basically, I'll make that assumption for the midterm, right? So again, for midterm, some people did a lot of scripting for the midterm. They basically scripted a lot of the different type of questions. You can do that if you want, but you still have to show your work, right? So think of how you would take the midterm as if you're in class, except that you have a computer available to you to do calculations, or you have a computer available to you to look up equations, but you still required to write down the equations you're using, right, for the midterm and the final. Okay, so it's not sufficient to write a line saying I Googled and I Googled and found some equation, and this is a result. That's not sufficient. You have to explain this is the equation you use. This plugging the numbers. This is a result from the equation, right? Okay. So that's still the expectation on the midterm. Okay. All right. So any questions? We can discuss. If no questions, we'll see you on Wednesday.
I have a question, Professor.
Sure. Yeah.
Could you go over one more time why the 240 volt coming into the house drops down to 120 when you put the neutral line?
Okay, right. Okay, so let's do that one more time. So what's that? Okay, so right. So okay, so you're home, right? So let's say you have a 240. So your home basically is all single phase, right? So it's very unlikely you live in a home that has a three-phase power supply. Our building, the ECE building, has three-phase power supply, but anything smaller is a single phase. So this is normally 240, line to line. Okay, but then how do you get to a 120 volts, right, in your home? Somehow you need to get to 120. So how you get to 120 is you put it through a transformer. There's some transformer. You still have two things coming out, except they're both referenced to a ground value now. So when you build a circuit, instead of two lines coming out, you have three lines coming out where you add a neutral. This is your X, Y, X, Y. What happened to my thing? Okay. X, Y. You have this transformer. You can think of all it does is adds a third wire as a center tapping the third wire. So we have a reference. We just reference to this neutral. So if you have basically if you have a 120 circuit, what you do is, so let's say you have a load. So your load is 120. You connect like this. Let's draw a little bit better. So your load is 120. The way it connects is it connects something like this. This is your load connection. If you have a load that's 240, so you have a kitchen or you have a stove that's 240, then you connect it. You connect it this way. Right, you connect it this way in your 240 connection. So this is sort of the wiring that goes down in your home.
So is that pretty much just saying that the neutral is like 120 volt almost?
Yeah, so it's easier if you make that 0 and think of plus minus 120.
Okay.
Right, because you can balance out. You don't have to just connect from Xn to a 120 load. In your home, there are basically different circuits. Part of it, a breaker maybe on X to neutral, but another part is Y to neutral. So those are 120 apart. So it's a bit easier to think of neutral as 0. And other things are all 120 away from it.
Okay.
So this is sort of the breaker circuit you have in your home. You have this.
So pretty much, when you start using the X to Y connection, you're getting 240, and so you can pretty much do double the current then, right?
Yeah, yeah. No, you want to reduce current, right? The higher voltage is to reduce current. You get more power.
Right.
So you need more power
with half the current.
Half the current, right? So you have, so your basically the box in your home is rated by current. Okay, rated by current. So what if your kitchen appliance needs more power or your washer and dryer needs more power? The way you do is you go up on voltage, right, to stay under your current limit.
Okay, that makes a lot more sense. Thank you.
Yeah.
I actually have a quick question about the homework.
Sure.
So homework number 3,